Okay, welcome back to linear algebra. We're going to try to finish up section 2.1 in this video lecture, talking about linear transformations, and in particular, talking about something called their null space and the range. So I want to give definitions of those. I want to look at some examples of how you determine the null space of a linear transformation. The dimensions of those things are called the rank and nullity, respectively. We'll make those definitions, and then I want to prove something called the Dimension Theorem. So it relates the rank and the nullity of a linear transformation to the dimension of its domain. And then I want to talk about there's three more theorems in the section, 2.4, 5, and 6. We'll state them below, but they're basically conditions that involve this null space and this range to determine whether your linear transformation is one-to-one or onto. So I won't review those concepts here in this video, but sometime you might want to stop it if it's not familiar to you, to remind yourself of what I mean by a one-to-one function, what I mean by an onto function. Okay, so we got a big program here. Let's get going. So first of all, these definitions. So if you're given a linear transformation, say T from a vector space V to a vector space W, it's from context, they're vector spaces, then by the null space of T, which is also called the kernel. We won't use that terminology much in this course, but lots of linear algebra books do and other subjects. So the kernel of a linear operator, the null space of a linear operator, it's the same thing. And in particular, it's a set. The notation for it is N of T. I would read that at N as null space, so null space of T. And it's those vectors in the domain that are mapped to the zero vector in the codomain. So I want to emphasize here in particular, the null space is a subset of the domain. It's a subset of V. It's those vectors that are mapped to zero. Okay, conversely, the range of T, which also has an alias, it's called the image. I prefer that terminology, but our book calls it the range. So it's also a set. R of T is its notation, R for range. And it's just the set of all outputs, T of V, where V ranges over all inputs. Okay, so the range is the subset of the codomain that is equal to the set of, I think of the codomain as possible outputs. The range are the possible outputs that are actually outputs. Okay, so null space and range of a linear transformation. Let's look at some examples just kind of briefly here. I've already written the details out so I can go a little bit quicker. But in our video lecture last time about introducing linear transformations, the very first example there, I'll use the same number, was a map from R2 to R2 given by that formula. T of AB is 3A plus B, comma A minus B. So if I wanted to know if something was in the null space, that's the question I'm asking. What's the null space of this linear map? Well, by definition, it's those vectors that are mapped to zero. Okay, but we have a specific formula for this map. T of x, if x is a comma b, is given by that expression. 0 is 0 comma 0. And the only way two coordinate vectors are equal like that is for their first coordinates to be equal. So 3a plus b has to be 0, and a minus b has to be 0. All right, so we get, in this case, two equations and two unknowns. In chapter 3, we'll study this systematically. Well, a minus b being 0 means that a has to be b. And then the first equation, therefore, then says that 4b is 0, which means b has to be 0. So it turns out that if b has to be 0 and a has to be b, then a and b both have to be 0. So the null space of this transformation contains only the 0 vector. I wrote it in vector notation there. If you want to write it as pairs, yeah, the null space of this linear transformation contains only the 0 vector. How about our second example from the previous lecture, the projection functions? Yeah, the projection of Rn onto R, where the pi sub j of x is just the jth coordinate, x sub j. Well, if you're in the null space of that, pi sub j of u is 0, so your jth coordinate is 0. So the null space just consists of those n tuples, those vectors in Fn, or Rn in this case, whose jth coordinate is equal to 0. Okay, it's the null space of that map. Skipping over the third one there, the transpose, I'm going to go, these are the same numbers as the video lecture before. The differentiation operator from polynomials of degree n to polynomials of degree n minus 1. D of f is f prime. What would be the null space? Well, it's those polynomials whose derivatives are 0. You know from calculus, the derivative of a polynomial, any function really, is 0 if and only if it's constant. So the constant polynomials end up being the null space of the differentiation operator. Okay, so there's just some examples. We'll talk more in detail about the systematic problem of determining the null space of a linear transformation, in particular determining a basis for it, but we'll save that for chapter 3. Now I'm going to start proving some results in here. The first theorem, I'm going to kind of go over the first part and then I'll leave the second part to you. Really, I wrote out both of them here, but the theorem 2.1 is the number. And it says if you have a linear transformation, both its null space and its range are subspaces. The null space is a subspace of the domain. The range is a subspace of the codomain. All right. To prove that, I'm going to prove with the subgroup test. Let's prove the first item. So I'm looking at the subspace test. I've got to show that 0 is in there. Well, t of 0 is equaling 0 shows that 0 is in the null space. And you might ask, well, why does t of 0 equal 0? It's because t of 0, you can think of it as t of 0 plus 0, which by linearity is t of 0 plus t of 0. Yeah. So then you can cancel. We're going to talk about this a little bit later too. Cancel t of 0 from both sides of that equation and you get that t of 0 has to be 0. Yeah, so 0 belongs to the null space. For closure under addition, if you take two elements in the null space and you want to know if their sum is, we'll take t of it. By linearity, t of the sum is the sum of the t's, but x and y are in the null space. So x and y individually are sent to 0 under t, and 0 plus 0 is 0. So the null space is closed. And then finally, if you take a scalar and an element of the null space, you want to know if ax is in the null space, take t of it. By linearity, the scalar comes out, x is in the null space, so t of x is 0. Anything times 0 is 0. All right? So that's closure under scalar multiplication. Show the null space is a subspace of V. All right? I'm going to leave it to you. I've got it written here, but I'm going to skip it. The range is also a subspace. And you prove it by the same three things. You have to show that 0 is in the range. We've already done that actually. That the sum of two things is in the range, and a scalar multiple of something in the range is in the range. So I'm going to leave that to you. I'm going to move on to the next theorem, theorem 2.2. So theorem 2.2, I actually want to introduce a little bit of notation. I'm going to back up a little bit here. If you have some set, here I'm writing it's a basis, or it doesn't have to be a basis, I'm using the same notation, but if you take some finite subset of vectors in a vector space, and you have a linear map, then if I write t of a set, so beta here is a set, I just mean apply t to everything in that set. Okay, so that's what the notation t of beta means. So with that notation in mind, let's take a look at this second theorem. So you have a linear transformation t from v to w, and you have a basis, beta of v. So v is evidently finite dimensional. It's got a finite basis. Then the theorem says that the range of t is actually the span of the image of that set. Right? So you take t of each one of the basis vectors. That's what I mean by t of b. Look at the span of that set. That is the same subspace of w that you get in the range. Okay. So this is a statement that says two sets are equal. So I'm going to show that they're subsets of each other. I'm going to start off by remarking that by definition, if I take t of anything in beta, I get an element of the range. So everything in this set t of beta is a subset of the range by definition. And since the range is a subspace of W, the span of t of beta is going to be contained in the range. Yeah. So that just to summarize that again, t of beta is contained in the range. The range itself is a subspace. So the space spanned by t of beta stays in that subspace by closure. Good. So that's one of our two inequality, our set inclusions. So now we have to take an arbitrary element of the range and show it's in the span. Fine. So let's just start writing the definitions. If we pick W in the range, well, then by definition, W is T of something in the domain. That's the definition of being in the range. Beta is a basis for V, right? So we have to be able to find scalars where we can write that V is a linear combination of vectors in beta. It's because it's a basis. Beta spans. In fact, these scalars are unique because beta is a basis, but I'm not really using the uniqueness right now. All right, well then I can take T of V. We know it's W by definition, but if we push T through this sum by linearity, T of V is equal to, the sum of the same scalars times T of those vectors. Each one of these things, T of V1, T of V2, and so on, they're all in elements of T of beta. So we can see that W is an F linear combination of elements in the set T of beta. It's in the span by definition. All right, so that's the opposite inclusion. The range is contained in the span. Above, we showed the span was contained in the range. And if two sets are subsets of each other, then they're equal. Cool. Pause the video and digest that. Write it up in your own, putting in detail. I'm going to just keep going here. So if you have a finite dimensional vector space V and W, both of them are finite dimensional in a linear map, well, since the null space and the range are subspaces of V and W, they're also finite dimensional. So I'm going to call their dimensions, respectively, the nullity of T and the rank of T. Okay, so the nullity of T and the rank of T, they're numbers. They're not vectors, they're scalars. In particular, they are the dimensions of the null space and the range. Okay, so those are some terminology, nullity and rank. So next term I'm going to state is the dimension theorem. Some people, I'm one of these people, they actually call this the rank nullity theorem. So if you see that out in the literature, it's a synonym for this dimension theorem. I prefer the name rank nullity theorem myself, but you'll see why it's called that. So what does the rank nullity theorem say? The dimension theorem, what does it say? If you take a linear transformation from V to W, they're finite dimensional. Well, at least V is. So I'm just defining its dimension as the number n. It's a finite number. Then the dimension theorem says that the rank of that transformation, the dimension of its range, plus the nullity of that transformation, the dimension of its null space, has to always equal n, right? So those two numbers have to add up to n. Here I'm just writing it without the terms rank and nullity. If you take the dimension of the range plus the dimension of what goes to 0, it accounts for the dimension of the domain. So it's kind of this balance. Take everything that survives T plus everything that was sent to 0 by T, and you must have accounted for everything. That's kind of an intuitive way to understand that theorem. Okay, let's take a look at the proof. I've got it written out, so I'm going to walk us through it fast. Pause the video after all of my statements and kind of ask yourself, why is that true? Yeah, so you can go at your own speed. Okay, so I'm going to take a subset called S of the domain, and I'm going to take it to be a basis for the null space. Okay, so I've got k vectors in it. K is evidently less than or equal to n because S is a subset of V. V has dimension n. So it's a basis for the null space. And then I'm going to extend that to a basis for V. Okay, so let beta be an extension. So I've got the same first k vectors, and then I extend that basis to a basis for V. Our work in chapter 1 in section 1.6 shows us that any linearly independent subset of a vector space can be extended to a basis. So in particular, this linearly independent subset can be extended to a basis. Okay, so keep in mind as you're reading this proof, the first k vectors of beta come from the null space. The rest of these were linearly independent add-ons to get us to span the whole space V. Cool. Okay, so then looking at this back half, starting with vk plus 1, if I take t of all of those things, I certainly would always get elements in the range. So all those things are in the range by definition. So first stopover spot, the span of t of that back half of the basis, I'm calling the vectors vk plus 1 to vn, the back half, so I don't have to keep saying vk plus 1 to vn. The span of the image of the back half of the basis is some subspace of the range. Okay, so now give me an element of the range. Take any vector in the range. Well, what would that mean? It means there's some vector in the domain that maps to it, right? Beta is a basis for the domain, so I can find scalars to write that vector v as a linear combination of my vectors in beta, right? If I take t of that v, Well, first of all, I get W. We said that T of V was W. What was W? W was any element in the range of T. So I take T of V, and then I'm just pushing T through by linearity, right? If V is equal to this sum, T of V is the sum of the same things. The scalars come out, applying T to each vector. But for the first K vectors in this sum, T of those things is 0 because the front half of this basis was a basis for the null space, right? So that's all I'm writing here is I've got a bunch of zeros plus the rest of this stuff. So W, an arbitrary element of our range, is actually a linear combination of T of just the back half of the basis. So that shows that W, which was T of V, is in the span of that back half of the basis. We already said that span was a subset of the range, so they're equal. Okay, so the image of the quote unquote back half of this basis beta, it's actually a spanning set for the range. Well, I actually claim that it's linearly independent. That T of Vk plus 1 through T of Vn, I claim that this is a linearly independent set. Okay, so how am I going to show that? Suppose I take some scalars, C1 through Ck plus 1 through Cn, and suppose a linear combination of those T's, T of the back half of beta is 0. All right, so that's a typical way to show they're linearly independent. I want to try to convince you that all these C's had to be 0. Okay, well, using the linearity of T, I can certainly rewrite that former equation as T of this thing is 0. Which means that that thing I just highlighted has to be in the null space, right? Ck plus 1 times Vk plus 1 all the way up to Cn plus Vn, that has to be an element of the null space. Look, T of it is 0. The null space is the span of the front half of the basis. So that means this linear combination of these V's that are part of this basis beta are linear combinations of other vectors in that basis beta. But that would be a contradiction unless all of the coefficients C's are 0, right? If one of these coefficients of C were non-zero, say it's this one, then I could solve Vk plus 1 in terms of the other basis vectors. That would mean that some basis vector, well, I'd have a dependence in my basis. That's a contradiction. So those C's all must be 0. So this set that we've already shown spans, it's actually linearly independent. So it's a basis for the range. Okay, so that tells us what the dimension of the range is. The dimension of the range is how many elements are in that set. Well, starting at k plus 1, you count up to n. There's n, take away k plus 1, or that's n minus k elements in that set. There's n minus k elements in the set that we just showed was a basis for the range. Okay, well, we already said that there were k elements in a basis for the null space, so the dimension of the null space is k. The dimension of the range we just proved is n minus k, and k plus n minus k is n. Okay, so that's how you prove, or one way to prove, this dimension theorem. And now you kind of see why it's called the rank nullity theorem, because, well, it's saying that the rank plus the nullity is equal to the dimension of the domain. Nice. Okay. So we're going to use that a little bit. The theorems 2.4, 5, and 6, I'm just going to kind of rip through them here. They're kind of theorems about how you can take advantage of this rank nullity theorem to take shortcuts on proving things like something is one-to-one, something is onto, and so on. Okay, so the first theorem, theorem 2.4, says that a linear map is one-to-one. Pause the video and remind yourself of what one-to-one means if you need to. A linear map from V to W is one-to-one if and only if its null space is the origin only. Okay, if and only if its null space is the origin only. All right, so it's an if and only if proof. Let's suppose that we have a one-to-one map. We know T of 0 is 0. Right, so 0 belongs to the null space, so we only have to show the reverse inclusion. It doesn't have anything to do with one-to-one, but 0 belongs to the null space. So if you take something in the null space, it means that T of it is 0. But since t of 0 is also 0, that means t of v is equal to t of 0. Well, t is 1 to 1, so that means v is 0. All right, so that shows that the null space of T is also a subset of 0. So those two inclusions together give us the equality. Nice. What about the other way? Let's suppose that we have some linear transformation whose null space is only 0, and I want to show it's 1 to 1. So a 1 to 1 proof should start like this. Take two inputs and suppose they have the same output, right? Take two inputs and suppose they have the same output. Well, then by linearity, t of x minus y is 0. Just subtract t of y from both sides and use linearity. But that means x minus y is in the null space, so it's equal to 0, right? But if x minus y is equal to 0, that means x is y. So the only way the outputs were the same is the inputs are the same. So t is 1 to 1. Nice. So it's kind of a shortcut. If you, instead of checking t of x equals t of y implies x equals y, this theorem is saying you can just check if t of x equals 0 implies x equals 0, then it's a 1 to 1 map. It's a shortcut. Theorem 2.5 has the same spirit. So you're giving a linear map from v to w, and the dimension of v and w are the same and they're finite. Okay, so that's the hypothesis. Then the following four conditions are equivalent. They're all true or they're all false. One of them is that t is 1 to 1. Another one is that t is onto. Let me stop for a second. That's kind of amazing, right? For a linear transformation between a vector space and itself, finite dimensional with the same dimension, if it's 1 to 1, it's automatically onto. If it's 1 to 1, it's automatically onto. Or if it's onto, it's automatically 1 to 1. Yeah, that's kind of neat. Those two things are both equivalent to the rank being the dimension of the domain. And all of that is equivalent to the dimension of the null space being 0. All right, so I'm going to try to walk you through an argument of this. You can pause the video as we go and think about everything that I say. So I'm going to just go quickly. First of all, the theorem that we just proved, theorem 2.4, says that 1 and 4 are the same. Because we just proved t is 1 to 1 if and only if its null space is the 0 vector. So in particular, t would be 1 to 1 if and only if the dimension of the null space was 0. Okay, so theorem 2.4 is actually the equivalence of 1 and 4. So now let me just try to do a little logic chain. What I'm going to try to prove to you here, I'll just sort of show you. I'm going to try to prove to you that that 1 implies 3, and then I'll try to convince you that 3 implies 2, and then I'll try to convince you that 2 implies 1. And if I can do that, then 1, 2, and 3 are all equivalent. If it's equivalent and 1 is equivalent to 4, the theorem will follow. Okay, so why does 1 imply 3? Maybe I can leave them there. I'm just going to do this super quick. Assume t is 1 to 1. Okay, well then because of condition 4, that means the null space is only the 0 vector. The dimension of the null space is 0. But since the dimension of the null space, let me actually write somewhere over here that the dimension of the null space plus the dimension of the range has to be n. Okay, that's the dimension theorem. So what am I saying in this first part of the proof? If the dimension of the null space is 0, well then the dimension of the range is n, so that the rank is equal to the dimension of v. Dimension of the range is the rank. Two numbers add up to dim v, one of them is 0, the other one has to be dim v. How about 3 implies 2? Suppose that the rank is equal to the dimension of v, which by hypothesis is the dimension of w. Okay, well, if the rank is the dimension of the range, the subspace of w. If they have the same dimension, they're equal. So if the range of t is equal to w, then t is onto by definition. How about 2 implies 1? If t is onto, well, then its range is w, so its rank is the dimension of w, which by hypothesis is the dimension of v. So back to the rank nullity theorem, if this number is equal to n, then the null space has to have dimension 0. If the null space has dimension 0 by part 1, equivalence to 4, the function's 1 to 1. All right, so this is a handy theorem. If you're looking at a linear map and you're interested in showing it's 1 to 1 and onto, if the domain and codomain have the same dimension, you don't have to do both of those. Okay, pause the video, soak that in. I'm just going to keep going. I think this is the last result of this long video lecture, Theorem 2.6. All of these things, they seem kind of random, but these are kind of important little tools in more interesting constructions we'll do in the future. So what does this one say? Given two vector spaces, and we take a basis for one of them called V, okay? So V has finite dimension n. And then you pick any subset of vectors in the other one, W. In fact, this subset I wrote W1 to Wn, but those things don't even have to be distinct. That subset S, it could be W1, W1, W1. It's just any subset of vectors in W that you've indexed with the numbers 1 to n, okay? And then the conclusion is that there is a unique linear transformation from V to W that sends Vj to Wj. So the spirit of this is that you have two vector spaces and you'd like to make a function between them. So you pick a basis for V, V has dimension n, and then you pick any n targets you want over in W, even if some of those targets are the same. Yeah, any n vectors in W with repetition allowed. And then there's one and only one function from V to W that's linear that sends the jth basis vector to the jth W that you picked. It's amazing. So in other words, linear transformations are easy to make. You can pick a basis for the domain and then have those basis vectors hit any targets you want, and you'll get yourself a linear transformation. So let me show you the construction. Okay, so how do you define this map? The key comes from the uniqueness in a linear combination of a basis. If you're given a V in this vector space, there's unique, and I'm going to emphasize unique because it's from a basis, scalars a1 through an, that your V is a linear combination of those things, okay? So no one can write V with different scalars. They're unique. So I'm going to just define this function by saying T of V is take those scalars, but just replace the vectors V with the vectors W in the same order. Replace V1 with W1. Okay, that gives me an element of W. I'm going to leave this to you, partially to give you something to think about and partially to make the video shorter. But by that definition, T is going to satisfy that equation for every U and V in V. I didn't quantify this very carefully. Let me do it now. For all U and V in V and all scalars C. All right, so in other words, T is linear. And I'll check this with you. By definition, T of Vj is Wj, because if V equals Vj, well, then you have to take Aj equal to 1, and you have to take all the other A's equal to 0. Right? When you go to write a basis vector in this form, you just have to take the coefficient 1 on that basis vector, kill the rest. All right, so by definition, T of Vj is Wj. Okay, so there's our linear map. That's the existence. And then there was supposed to be only one map. Suppose you had some other linear map, T prime, and it satisfies this for every j. Okay, well, then if you give me any vector, write it as a linear combination of the v's, push through by linearity, you'll see that T does the same thing to that vector as T prime. It's going to happen because they do the same thing to all the VJs. All right, so that's just by linearity. Maybe I'll write that out. Well, I've got a corollary. So if I were to write this last highlighted expression out, T of V, we're writing V as this linear combination. So you push T through by linearity. right? But T of Vj is T prime of Vj for every j. So I can replace those T's with T primes in every single term. And then by the linearity of T prime, so that's what I mean by bilinearity. T of V is equal to T prime of V. Nice. Okay, last thing I'm going to say, I'll just leave it to you to think about why this is true. This is a very convenient corollary for us. We'll use it all the time. If two linear maps have the same value on a basis, then they're the same. Two linear functions that do the same thing to every basis vector does the same thing to the whole space. Okay, that was a lot of material. I hope you stopped and thought about it a lot. Thanks for listening.